In some of the videos that you watched when doing the transmission line study, I alluded to some issues involving the frequency that we were running the function generator at, and I would like to address those now in this video, what that was about. So we know, for example, the key relationship between wavelength and frequency is that C is equal to lambda times F. And if I solve this, for example, for the frequency here, I would get C over lambda. So in other words, I can calculate frequencies based on the speed of light and whatever wavelength I happen to be discussing. So let me just put a few numbers out there so we can seed our discussion, and they're just solutions that come from using this equation here. So basically, I would get about 150 gigahertz for a frequency of a wavelength of 2 millimeters. I'd get something like 60 gigahertz when dealing with a wavelength of 5 millimeters. I'd get something like 4 gigahertz when dealing with a wavelength of about 80 millimeters. And lastly then, I would get a frequency of about 1 megahertz when dealing with a wavelength of 300 meters. Okay, so these aren't any sort of magical numbers. They just sort of come by plugging these wavelengths here in for a wavelength here and just solving for the frequency that you get. So what does this have to do with our lab? Well, something that you may have never thought about before, but when you do electronics, for example, like say you're building an electronic circuit and you have a resistor that you're using in the circuit like this. So here's the resistor here, and you might have some color codes on there, I don't know, like red, orange, or something like that. You might be building a circuit. Well, this resistor here, the core resistive element that you have in here, has a length of about 5 millimeters. And the entire size of the resistor like this is something like maybe 12 millimeters, so, and start adding the leads in there. And so what does that mean for you? Well, what it means then is, supposing in this electronic circuit you were imposing some sort of sine wave voltage on your resistor. Then what will happen then is, suppose you started to approach wavelengths that this formula predicted here, or frequencies that this formula predicted. So because the resistor, let's say the core resistive element here, has a size of about 5 millimeters, that 5 millimeters corresponds to a frequency of about 60 gigahertz. And so what that would mean then is, if your frequency here started to approach 60 gigahertz, then you might get some strange resonances in the resistor material that you didn't anticipate. Like, for example, it could very well be that you might get a harmonic of the 60 gigahertz sort of existing between the attachment points in the resistor where the lead attaches to the resistive element on both sides. You might get some harmonic resonating in there. And that could sort of have some bad ramifications for your circuit, because as soon as you get a little resonating in there, you might get some energy going back this way towards the source, or some increased energy coming out that way. Or you could even get a higher harmonic sort of existing in there, maybe that looks something like that second harmonic, maybe looks something like that. It might just fit inside the resistor. And these resonances here, they can be bad, but they sort of bring some question marks up. They might start introducing some undesirable effects in your circuit for reasons that would be difficult to diagnose. But it might very well boil down to the fact that you are choosing a frequency, say 60 gigahertz here, that is just beginning to match some of the sizes of the components in your circuit. And for example, suppose that this is something you're definitely maybe familiar with here. You might be using a breadboard. The nice sort of white thing here that has all those little holes in it and things that you can attach your components into. Well, the breadboard itself has a size here of about 80 millimeters. And you can go about with all your wiring, things like that. Maybe you have green wires going like this, and you get some purple wire going like that. And maybe you have a capacitor sitting in here like this doing something. There's a capacitor sitting in there, and maybe you have one of the resistors going through some other holes over here on this side of the circuit. You just built your circuit. Maybe you even have like a integrated circuit in here that has those, so that black case in there might be sitting in there, something like that. Well, you're in here in this 80 millimeter size of the breadboard, and so what that means is the extent of your circuit would sort of have to be 80 millimeters. But if you scroll back up again, you can see that 80 millimeters corresponds to around 4 gigahertz, sort of even a lower frequency now. So it turns out that whatever you're doing, if you're in your circuit here, if you sort of impose some sine wave on it, like maybe you fed a transistor or a capacitor or something with a sine wave here, you better sort of keep this frequency less than 4 gigahertz. If you want sort of things to behave, let's just say, quote unquote, normally. And I don't even know what that means, but if you sort of wanted your circuit to behave the way you're anticipating it you might want to avoid frequencies like that. Now, you probably never had to think about this before, because commonly in sort of undergraduate electronics, we do a lot of DC electronics, of course, and that's just a frequency of 0. So you're nowhere near any resonance or anything like that. But it would be possible when you start doing filter labs and things, you might start putting sine waves on your circuit. But even in, say, our lower division class, our frequency 0 is sort of well below even 1 megahertz. We'll never go anywhere near gigahertz or anything like that. But it's just something to keep in mind. Now, what does this have to do with the transmission line lab? That's sort of the general idea I'm trying to get across here. The transmission line. Well, the transmission line was a long piece of coaxial cable like this that had a length of about 300 meters. It was 1,000 feet, right? 1,000 feet. And the 300 meters or 1,000 feet, well, that corresponds to a frequency of like 1 megahertz. Very sort of digestible frequency in there. Remember, the frequency of this is sort of like 1 megahertz. So what that means is when I deal with a transmission line, if I wanted things to behave sort of predictably, I better sort of avoid things. I really should choose any driving frequency to not just be less than 1 megahertz, but maybe much, much less than 1 megahertz. Because what I do not want to happen, say with a sine wave that I might have injected into my transmission line, which we did in this lab, is I don't want these harmonics to start happening. I don't want these resonances to start happening. Like I don't want the transmission line to look like that, or I don't want the transmission line to start sustaining like resonance modes like that, because that's where this unpredictability of the circuit might come from. And I think we hit that at least a few times in the circuit. So what I tried to do is we were running the circuit. I was probing around looking for resonances, and I did see some sort of odd behavior. I think you might have seen them as well. But what started to happen is I definitely approached, oops, that's really going to be a little thick there. I definitely approached some frequencies sort of near about 500 kilohertz, which is about halfway there, and that was just a bad thing to do. You want to stay away from that. Remember, I wanted all my frequencies to be much, much less. I don't need to write it again. I have it right here. I want all my frequencies to be much, much less than 1 megahertz. And by much, much less, I'm going to say something like maybe any maximum frequency that I want to trust or any take some data from is going to have to be, I don't know, something like maybe 100 kilohertz at most. Okay, at most. That's the closest I want to be. And I think when I approached some of these frequencies, we did see some strange things happening. Like I can remember one very clearly where we're mapping out a resonance as a function of frequency, and the data definitely went up like this, and it definitely went down and maybe started to come down. But as I started to increase even more and more, it started to go back up again. And this point here was always something around a number like this. It was around this area right here. So I just want to avoid that, because this might be a case here where we're starting to stimulate some strange resonances in the coaxial cable itself. So that was sort of a limitation in some of the frequencies that I was sort of allowed to use to get some reasonable results from the transmission line lab. So just keep that in mind, that there are some ramifications for the sizes of your components and the things you're building your circuit with relative to the frequencies you might end up driving your circuit with eventually. And it's just the good old wave on a string analogy. You want to avoid these resonances popping up either at large scale in a big transmission line like that, or even at a smaller scale like this. If you have some discrete components in your circuit, you certainly don't want any strange resonances in the input of a capacitor or in the resistive material of a resistor, or even across the entire breadboard itself. Like you wouldn't want some standing wave of voltage sitting here like this across all of the elements in your circuit. But at, say, an 80 millimeter breadboard, that could certainly begin to happen if you drove it at 4 gigahertz, something like that. So anyway, that's what that sort of strange effect was in the transmission line lab. And the last word on this is that you want to treat the line, the entire transmission line, as a lump in the circuit. So a lump in the circuit, that means like you want it to behave like a discrete element, like a capacitor like this, or like a transistor in those little black cases, just sort of a discrete lump or discrete element, to avoid those resonances. And the way, of course, I do that in the coax labs, I keep my frequencies much, much less than 1 megahertz or so.